time plus 1/2 gt squared. But the original vertical velocity, if you shoot it horizontally, is nothing. It's all horizontal. There's gonna be two problems on there that do this. You're gonna launch something horizontally. You're gonna have to do one of the two counts, the other's bonus. We're worried about the 45-minute time interval here. A test in 45 minutes is just disastrous after the first one, and it's because it's such a short time frame. So Davenport said, let's do two problems. You have to pick one, and then come back and do the other for bonus after that. But you only have to do one of the two. You get to pick which one of the two you want to do, and then we'll go on and we'll have some projectile type of thing going that way too. So it's going to be shorter than it would have been if we had more time, but we don't. And so when it's being shot horizontally, the vertical velocity is 0, and anything times 0 is 0, so it's 1/2 gt squared. So the height, if the marble falls, when she shoots this marble, is going to be 1/2 of gravity, that's 5, half of 10 is 5, times 0.156 squared. Here's the thing that people forget to do after they get going here, is they take and they forget to square right there. They just do grab 1/2 gravity times time. It's just the things you start doing when you are getting better at this is you just forget to square that darn thing. Now, the other thing people are asking me is, do I have to square the 5 first? If you type this in your calculator, like this, 1/2 times 10 times 0.156 squared, your TI-30 or better will know the order of operations, and it will take care of you. You just type in 0.5 times 10, or 5, times 0.156 x squared squared, you just square it, and then equals, make sure you hit the equals, it'll tell you what it is here. So you just type in 0.5 times 10 times, see, it hasn't even calculated it yet, 0.156 squared, boom, 0.12 meters. It will fall 12 centimeters. So when they sight a gun, when you have a gun sight, they don't shoot directly at the target, because if they aim just straight at the target, it would fall away, it would miss the target. So when they sight the gun, that has a itsy, not a lot, because the bullet's going pretty fast, but when they sight that, it's actually going in a little parabolic path for the distance that you have when you're doing this. And so it just has a smidge, and really what they do, my son used to do this at Randsburg, he would sight the guns and he'd shoot at the target very carefully, and if they were all shooting left and low, he'd adjust the sight so that when you aimed at the target, you're looking straight at the target, you would hit the target. But really what it's doing is when they put that sight on there, it's just set so that the tip of the gun is just on a smooth. Other things, the unit dimensional analysis. Again, if you come up with 40 seconds, that's like forever in these things. Mostly just common things. And so, yeah, I kind of put together what went on. A lot of getting horizontal and vertical interface. Horizontal's horizontal, vertical's the vertical, never the twain shall meet. So keep your X's as X's and Y's with Y's. I call it secretarial. It's about bookkeeping. Just make sure that you're thinking this way's horizontal, this way's up and down. Horizontally, distance equals rate times time. Vertically, it's all these equations going on. So you've got the Y velocity. The average velocity is equal to the change in distance over the change in time. The acceleration is the change in velocity over the change in time, and vertically it's gravity. I like to think of this as V final equals V original plus acceleration times time. Your average velocity is that very mono-purpose kind of thing that's original plus final divided by 2. Your distance in the Y direction equals the original Y times time plus, if you're shooting up and down, minus 1/2 gt squared. And then this last one is the V final squared is equal to V original squared plus 2A delta Y, G delta Y if it's in the Y form. Now, look at this. you could have done this. We'll do this on another. But you could have found out how far it fell. Once you have the time, you could get the speed that it's going when it gets down there, because it's going to be moving down at a little bit of smidge. It's still got its 16 going this way, but it's going to be traveling 1.56 downward. Acceleration is VT. V final equals acceleration times time, 10 times this time. Means it's going down at 1.56 meters per second, and so you've got a total velocity, kind of a hypotenuse thing. That's where the x and the y meet, is when you're doing x, when you want to find the total speed or the direction as you do that. Let's do, what I had wanted to point out, and a few people were figuring this out, and I showed them when we were doing the lab, was this. Out to the left of the equations, there's this gobbledygook here in parentheses. And it's like, what is all that? Well, these are the variables that are in this equation. So if you have a problem, let's do one. Off worksheet 5, let's pick one. Number 10. No, that's still a one-dimensional problem. 13. No. Let's do. Sure. Number 12. We've already done 12, haven't we? Okay, let's not do 12 again then. Let's do one of these big boys. Do we have a launch thing? Man, not a lot of problems. Pull up and do another. 13. A golf ball is driven off the tee at 50 meters per second and an angle of 30 degrees above the horizontal. So here's 13. You're hitting a golf ball at a 30-degree angle. First, this is the last part of the test. After you do horizontal projections off of houses, bridges, whatever, there's a projectile problem. You hit a golf ball. What are the horizontal and vertical velocities on this thing? Those are the sides here and here. So it's 50 cos 30 and 50 sine 30. Opposite side, the y part's always sine, the x part's always cos, and so this is going to be 43.3 meters per second, and when sine of 30.5, this is going to be 25 meters per second. So what are the horizontal and vertical velocities? Horizontal 43.3, vertical's 25. Now, then it goes on to say, for how long does it rise? Look at what's going on here. So we want to know a time. We want to know time. How long does it go up for? So we need t. We have the original velocity, 25, in the y direction. So we have that. We have gravity is 10. It is slowing down at 10 meters per second every second that it goes up for. And what's the final vertical velocity at the very top? How much is it going up and down when it's at the top? Right? No. Right? No. Or even if it was going straight up. No. The vertical velocity at the top is 0 because it's going from going up to going down. It's slowing down, slowing down, slowing down, and then it's picking up speed. If we did a graph of the y velocity as a function of time, when it leaves your hand, when you hit the golf ball, it's moving really fast. It slows down, and then it starts picking up speed in a negative direction. It would look like this, and right at the top, it's right there. It's passing through 0 instantaneously. So we know the velocity final. Find an equation that has acceleration, original, final, and time. It's right here. Look, v final, v original, a, and I want to know this one. What these are here for is that you don't have to look at the equations. You can look at what's in the equation. And if I have 3 of these things, I can find the 4th. If I have 2 of these, I can get the 3rd one. If I have 3 of these things, I can find the 1. It's one equation, one unknown. If I want to find the acceleration and they give me the distance it travels, the original speed, and time, then I can find the acceleration right here, the acceleration will be that. I have to do a little algebra. This is the algebra 1 stuff. Distance minus original velocity times time equals 1/2 AT squared. Then I multiply by 2. You multiply if it's divided by it, you divide if it's added. And then you would divide by t squared, and that would give you the acceleration right there. So you can go dig it out. I call these the basic equation. And then when you rearrange them to get what you want, that's called the working equation. And then you shove the numbers in and see what kind of number you get, and if it makes sense when you do that. So here, their question was, for how long does it rise? That's the time up. You have an equation on the front that says time up in a box kind of thing. Or we can just solve for it. Look, acceleration is change in velocity over time. Time is change in velocity over acceleration. There's our algebra. And so it goes from 25 to 0, slowing down at 10 per second. 25 divided by 10, it's going to go up 25 minus 0. It's really 0 minus 25, final minus original, all over negative 10 meters per second, because it's slowing down by 10. And the negatives cancel out. So it comes out to be 2.5 seconds that it goes up for. So now we know the range time, because it's going to go up for 2.5, and there's some symmetry going on here. It's going to fall for 2.5. The total time of flight is going to be twice the time up. It's going to be 5 seconds in this problem. So the time up is 2.5. Once you get time, that's when it's like beautiful. Okay, he gave me time. That's great. Once I get time, I'm good. Now, here again, here's where partial credit kicks in. If you botch the time and you get 0.8 seconds, then it's going to look like it only stays in the air for 1.6 seconds. But you can still get credit for those future things, but answers start getting kind of weird if you do that. So, how long does it stay in the air? 5 seconds, twice as long. Then how far does it travel before bouncing on the fairway or green? That's called the range. That's the total distance it travels. You would take horizontally, distance equals rate times time. Horizontally, distance equals rate times time. Horizontally, distance equals rate times time. Vertically, you got these 5 things going on. So it's just going to be 43.3 meters per second. The horizontal rate, this is v sub x, times 5 seconds. That's going to be 215 and 1.5. 216.5 meters. There are other ways to do that. You could use the range equation. On the front of the test, there will be a range equation in a box. And it says it's v original squared sine 2 theta all over g. You can plug it right into here. Now here's where you got to be careful, because this v original is the 50, not 43. It's like the speed when you hit it. So that's going to be 50 squared times the sine of twice 30. That's 60. Sine of 60 all over 10. Look at the units. Meters squared per second squared divided by meters per second squared. It will come out into meters. 2500 divided by 10 is 250 times sine of 60, 0.866. Use a calculator. And so it's going to come out to be 216.5. It's going to be the exact same thing when you do it. So you can use the range equation or distance equals rate times time, using the total time for it to get back down to the ground. Then it goes on to say, well, what's its maximum height? This is the tricky one, because we're looking for delta y. So look, if we're going through here, we don't want to, this is not a bad one right here. Look at this. The average velocity, it goes from 25 to 0. What's the average of 25 and 0? 25 plus 0 divided by 2. Half of 25 is 12.5. So the average velocity is 12.5 meters per second, and it's doing that for 2.5 seconds, the time up. If you did that, that does give you the height that it gets to in that time. That's like 31.25 meters. You could do it that way. You could do it this way. Look, the final velocity at the top is 0. 0 squared is 0. The velocity original, this is vertical, this is y, so it's 25. So 25 squared, that's 625, plus 2 times, here you have to be careful with the minus sign, because gravity's down at 10, so it's going to be minus 10. Otherwise, you have this minus thing over here and you square root it or do something with it. You get a negative number, but it's going to come out positive, times delta y. When you take 625 divided by 20, so it becomes negative 625 meters squared per second squared over negative 20 meters per second squared. You get meters, and you get 31.25 meters. Same answer. And the last one is you could use this one right here. What's the height when it gets up there? You take your 25 times 2.5 seconds to get there. Take away, here's the part, it doesn't go taken off like that. 1/2 times 10 times 2.5 squared. Half of 10 is 5. 5 times 6 1/4. This is 31.25. But 25 times 2.5 is 50, and 12 1/2 is 62.5 minus 31 1/4 is 31.25. You get the same answer no matter which way you go. There are more than one way to get there. Because when we took these 3 starting equations, this is what we started with, and we derived these other ones, so you can do it a roundabout way. I always say the best solution to the problem is the one that you see. I'm given this, I want this, what can I find? You find that, and then you go from there. If you document what you're doing, you get points. I mean, if you're like distance equals rate times time, make sure you're not using the average rate. Too many velocities. Don't use the original speed as the average speed or something like that. But if you're documenting, that's okay. The one I can't give points for, it makes me cry, is if somebody takes this and instead of doing distance equals rate times time or velocity is distance per time, if you go like time, I don't even want to write this down, equals distance times rate. That's one of the things I have on that, oh my gosh, that post-mortem on the test thing. That is wrong. Because that's going to give you meters times meters per second. It's going to be meters squared per second. And you're not going to get anything right with that, dimensionally or otherwise. And so when I'm grading this thing, I have a calculator in my hand. And if you get the wrong time, but you do everything else right, it's like, okay, they just had the wrong time, but it's, reasonable, so good. You don't know a good reasonable answer, you get points. But if you have this, and then you work that problem, I'm looking at that and I go, that is not correct. I don't even want to write it on the board. And if you do that, and then you go from there, it's like, there's nothing right on the piece of paper. I have nothing I can give you a point for. I'm always looking for a way to give you a point. If you give me an equation, it's a starting equation, a basic equation, I'm like, yeah, that's how you do this problem. Then you do the algebra. If you botch the algebra, that's an algebra mistake, not a physics mistake. And so I'm like, okay, that's a point. A lot of times people will get the reciprocal of the answer. So it's supposed to be 2, but you get 1/2. I'm like, oops. I'm thinking you flipped your distance and your time when you shoved them in there. So either you plugged the wrong guy in for the right thing, or the wrong thing, or you somehow got this flipped over when you were doing your algebra, and flipping it over, getting the reciprocal, that's like a point out of 3. It's like, okay, so they botched it, they got the reciprocal of the answer. So be showing me what you're doing. Put a little bit of that stuff down on the paper, because that helps out. Do you guys have anything you want to see off of worksheet 5? That's most of it. We'll do some vector stuff tomorrow. Be working the worksheet, because that is pretty much the test. It's going to have some one-dimensional stuff, and go back and work your first test. Be working it, because that way you can practice up those types of problems. That's what you're supposed to do, is kind of go back and fix the darn thing so we can do a little bit better on this next one. There we go. Favorites of any kind? Yeah. Number 17 is a good one. An ugly thing, but a good one. If you can do number 17, you're going to be sitting good. Because number 17 is it's a bit of work. You're given what are we, hitting a golf ball or something like that? Kicking a soccer ball, and it's going off at what speed? Okay. Now, the big angles that you're going to get. 45, 45 is a good one. 45, 45, 90, because that means this side equals that side. And then it's an okay problem. Other angles that are pretty good. 37 and 53 and 30 and 60. A 37, 53 right triangle has, it's a 3, 4, 5 right triangle. So if this is 25 and it was 37, 25 cos 37, 4/5 of 25, this would be 20 meters per second, and this would be 3/5 of 25, this would be 15. So I like 3, 4, 5s, a nice 37, 50, you'll see a lot of 37s and 53s, because then if it was going the other way, you're hitting the soccer ball this way, that's a real lob. When you do it that way, then if this was 25, this would be 15, and this would be 20. You'd hang in the air a little bit longer, but it wouldn't have as much horizontal rate. So 3753, and the other one 3060, because a third sine of 30 is 0.5. And the other one's sine. So here's a 45/45. So the way you get the horizontal and vertical components, you just take hypotenuse times the cosine of 45, and hypotenuse times the sine of 45. The y part is always the sine, the x part's the cosine. We're going to give you the angle of the horizontal. Cosine of 45 is 0.707, so this comes out to be, I don't know what this comes out to be, 17.7, I'm guessing. 17.7, and then this one's going to be 17.7 as well, because it's an isosceles rectangle. When you do 25 sine, so now this is your original x, or your x velocity, and this is your original y velocity. So the best way to graph the position versus time is make yourself a little t-chart. Time, horizontal distance, vertical distance. Horizontally, distance is just equal to the rate times the time. So it's going to be 17.7 times t. Vertically, I just got rid of that equation. It's going to be original y times time minus 1/2 gt squared. So it's going to be 17.7 times t minus 5, gravity's 10, t squared. A really good number to pick. I love this one. 0. 0 seconds. 0 times anything is 0. 0 times something plus 0 squared times something, 0. When you first launch this thing or kick it, it's right at the origin. It's right there. But do 1 second. 1. I like 1 second. 1 times 17.7 is 17.7 meters. 1 times 17.7 minus 5 times 1. 17.7 times 1 minus 5 times 1 squared. That's 17.7 minus 5. That's 12.7. 2 times 17.7 is 35.4. 2 times, it's going to be 35.4. 17.7 times 2 minus 5 times 2 squared. 35.4 minus 20, 15.4. 3 times 17.7 is 51, 52.1. 52.1 minus 5 times 3 squared. That's 9 times 5, 45. 52.1 minus, it's gonna be about 7 and a smidge, whatever, use calculator. Now, there's some other numbers that are nice. The time up. Look at what we're doing. We're kicking this at 17.7 up, and it's going to 0 at the top. How long does it take to go from 17.7 to 0, slowing down at 10 every second? The time up is just equal to the original y velocity divided by gravity, 10. It takes 1.77 seconds to get to the top. So if you put in 1.77, uglier number, but 17.7 times 1.77 minus 5 times 1.77 squared, this height will be right at the crest, right at the highest point that it's at. And that comes out to be, I believe, on the y direction, 15.7. Note, just a little, at 2 seconds, it's a little bit lower. It's on its way over. Let's put these dots on here. So we got 17.7 and 12.7. Here's 10, 20. You won't have to graph like this on there, but if you can do this one, you're sitting pretty good. 10, 20, 30, 40, 50, 60. And it's 17.7, 12-ish.7. And it's at 0, 0. And it's at 35.4 and 15.4. But that's already on the way back down again, I think, because it's past the 1.7 second marker. So where is it? Oh, that's 17.7 times 1.77. 17.7 times 1.77. 17.7 times 1.77. It will have traveled across, and I will have fat fingers. Let's calculate anything with batteries. 31.3. Now the reason I like to do the time up is it's over here at 31.3 and it's at 15.7, so it's like right there, just a little bit higher than that. But look at twice the time up. The total time of flight. It goes up for 1.77, it comes down for 1.77. And so the total time of flight is going to be at 2 times 1.77, 3.54 seconds. And the height when it gets back at 3.54, oh, 15 is here, actually. Here's going to go. That's when it's right back on the ground. So when you do this number over here, if you take twice the time up, your y height is going to be at 0 because it's back at the bottom again. Goes up for 1.77, it gets to 0, then it falls back down to the exact same height to get back down to the ground, and it speeds up back to the exact same vertical speed. So it goes from 17.7 going up to 17.7 going down. It's going 17.7 across. And so this thing's going to hit the ground at the same speed and angle that it left the ground at when it does that. And so, but that's a good one because then it's just twice as much. Because it traveled for twice as long, that's 62.6 meters across. And look, you got your dots. And any dot that you have that's in under 3.54 seconds will be on this part of the parabola right here. Pick a number like 4 seconds, and it's going to end up down here. It's as if there was a cliff here. It's either going to bounce, and we're not doing any bouncing, or it's gone down below here, and now you're picking up speed and going further and further down. It is a parabola, parabolic path. It's just that once you get below 0, now you're just going to have to keep on going that way, and you'd have to be on a cliff or something like that. So, if you do this one, you're doing pretty good. Now the other one is this, and watch this. This is good, because a real place to make a mistake is they go, what's the speed of the object, the soccer ball, at the very top? And you're really tempted to say 0 because it's at the top, but look, that's true if you do this, if you kick it straight up. But if it's going across, it's still moving at 17.7. It's going 17.7 here, 17.7 here, 17.7 there, 17.7 there. Horizontally, at the top, the y part's 0, and other places, it's still gonna have a little bit of y velocity. You're always moving in the direction that you're moving. You're always moving tangent to this curve. Even when you hit the ground, you're going in the direction that you're going. You know, and so you're gonna have some horizontal and vertical, but right at the top, you're still just gonna have your original horizontal velocity coasting across as it goes, kind of thing. So be careful about that. They even like to ask that one on an AP test. Somebody kicks a soccer ball, what's its speed at the top? Its speed at the top is this horizontal speed right here, because your y part goes to nothing, and you're still coasting across doing that.